Hi everyone, today's video is on single degree of freedom free and forced vibration system part 2. In part 1 video, you were introduced how to derive general equation for free and forced single degree of freedom vibration system and how to find natural frequency of undamped, damped, free and forced vibration system. After watching part 2 video, you will be able to solve linearized equation of motion for these three cases and draw vibration signal responses in time domain. So for undamped free vibration, if we divide J equivalent both sides, we get this kind of form where omega n being the natural frequency of the system, while for damped free vibration cases, if we divide again J equivalent in both sides, we get this kind of form where zeta is being damping ratio, and the final form of equation is called homogeneous ordinary differential equation. General solution of this homogeneous ordinary differential equation is theta t equal theta e to the power lambda t. If we take first and second derivative of theta and substitute this value into equation of motion, then we get this kind of form where we can see that theta and e to the power lambda t are not zero. Then this part must be zero, which is a quadratic algebraic equation solution. So we can see that lambda will have two values. So the solution will have two parts consisting of theta 1 e to the power lambda 1t and theta 2 e to the power lambda 2t. So this solution strongly depends on zeta values. Let's consider four possible cases, starting with case 1, where we consider undamped free vibration, where damper is absent, so damping coefficient C torsional equivalent and damping ratio zeta will be 0. So we get lambda has two values which are purely imaginary numbers, and for that we get the solution as a function of cosine. So the curve will have cosine function as cosine curve with period t equal to pi on omega n, and which will last forever. Next case is for damped free vibration, where zeta is in between 0 and 1, so C torsional equivalent will be more than 0 and less than 2J equivalent omega n, and this case is called underdamped case. In this case, the lambda will have two complex conjugate values, and using Euler formula, the solution of this case will have negative exponential part and cosine part. Here omega d is the damped natural frequency and phi being phase angle. So in this case, the curve will look like this, where we can see the vibration is harmonic and it fades away due to the negative exponential part, and it has period equal to pi on omega d. In third case, zeta is equal to 1, so C torsional equivalent will be equal to 2J equivalent omega n, and this case is called critically damped case. In this case, lambda will have equal real and negative value, so the solution will have a negative exponential part, and the amplitude of this curve will decrease very quickly, and there is no oscillation and periodic motion occur. For fourth case, where zeta is more than 1, so C torsional equivalent will be more than 2J equivalent omega n, and this case is called overdamped case. In this case, lambda will have two negative real values, so the solution will look like this, and the amplitude of the curve will decrease quickly, and like critically damped case, there will be no oscillation and periodic motion. Next case is for force damped vibration, where the equation we get is a non-homogeneous second order differential equation, and the solution of this equation is the summation of theta h and theta p. Theta h being this homogeneous or complementary solution of free vibration equation, and theta p being particular solution, and its frequency is as same as the frequency of force or moment. Homogeneous solution will die out due to the negative exponential part, and which is a very common phenomenon in true engineering cases because of damping, which is unavoidable. If the time is long enough, then the homogeneous solution will disappear and the final force vibration will continue. This curve represents force damped vibration motion, and this curve represents particular solution of the vibration. This is a steady state and it will continue, while this part is the transition solution or homogeneous solution, which will fade away eventually. So we are now more interested to get the amplitude of a particular solution, theta p. To get the amplitude of theta p, we need to substitute theta p first and second derivative of theta p into the equation of motion, and then we get this kind of form. Then using properties of cos omega t plus phi p and sin omega t plus phi p, and separating the terms into in sin omega t and cos omega t, there are two equations that can be obtained, and from them one equation shows this kind of form. If we consider the amplitude of theta p equation, and if we consider that force frequency omega is equal to natural frequency of the system, then we get greater amplitude, which means that the system will vibrate heavily, and this phenomenon is called resonance, which may cause catastrophic failure of some in case of some structures. So in some cases we want to avoid this resonance. Alright, so from this video you have introduced how to solve the linearized equation of motion for three cases: undamped free vibration, damped free vibration, and damped force vibration, and how to draw vibration signal response in time domain. Thanks for watching.